Hi, my name is Victor. In the last episode, we discovered the discrete Fourier transform, but there was still one question left. Why are we confined within the frequency range that we can analyze our signal? Well, in this episode, I'm going to answer that question. If you haven't yet, go get yourself the software I wrote. You can get it via the link in the description below. Okay, let's go! For that, we will go to the Aliasing tab. In the Aliasing tab, you will again find a generator, which has the typical controls, which produces this green signal you see right here. So we have a frequency and a phase, and also an amplitude. You can also switch between different wave shapes. Okay, let's suppose for a second that this is a continuous signal. Technically it is not, because the computer can't really save continuous signals, of course, and this program runs in the computer. So it is technically discrete, but let's suppose for education's sake that it is continuous for a second. And then we have a sample rate, which determines how many samples we take of that continuous signal to produce what you see down here. Down here you see the exact same samples, which are interpolated linearly. Technically, this linear interpolation is not what happens when converting your digital signal back to an analog signal for your speakers to play it. You would rather use something like a Lagrange interpolation, which is a whole other topic for another time. So if you are interested in it, go look it up yourself. I encourage you to do so. Okay, so now let's experiment with this whole thing. First of all, let's set a fixed sample rate of maybe 30. Okay, so there are 30 samples right in this window. And now, let's turn up the frequency and see what happens. Let's press Alt to make fine adjustments. And you will see, well, it looks pretty good. It looks a little bit edgy, but that's alright. We can still see how the frequency looks like. Let's push the frequency further. We push it further and further. And at some point you will see this kind of beat frequency, which is the third time that we notice this exact phenomenon. Let's push the frequency a tad bit higher, and we will get to a point where the frequency is exactly 15, so half the sample rate. You will see that the points are pretty much at zero the whole time. They would be at zero if the green signal was perfectly continuous, but it's discrete, as I said, and this gives us a little bit of an artifact right here. But yeah, all these points are at zero. All the samples have values of 0. As you can see, we have exactly 2 samples per period of our input signal. And as we shift the phase, suddenly these 2 points align exactly with the highest points of the period. The frequency is 15, which is exactly half the sample rate of 30. This frequency is called the Nyquist frequency. At the Nyquist frequency, we have a point of ambiguity. We can not reconstruct the ingoing signal anymore according to the discrete signal that we saved. And that's problematic, because depending on what phase we are at, the amplitude is totally different. But what happens if we push the frequency even further than that? When we push it further, we again get this kind of beat frequency. Let's push it even further. And then there's a lot of sample chaos, and I can't really discern what's happening down here. But let's push it further and see what's really happening. At some point, you will see there's a totally different wave appearing right here than the input wave that we set above. This frequency has been mirrored at the Nyquist frequency. Any frequency that goes beyond the Nyquist frequency gets mirrored down again. So for example, if we set this frequency to 26 exactly, 26 goes above the Nyquist frequency of 15 by 11. So we have to mirror that. So 15 minus 11 gives us 4 again. So down here we get a signal with a frequency of 4. Let's count the periods. 1, 2, 3, 4. That matches up perfectly. Okay, but now what happens if we push that frequency even further? The frequency of the output decreases as I push the frequency higher. And at some point, we get this. This happens exactly when the frequency is the same as the sample rate. Both are 30 at the moment. Because the green input frequency is not continuous, it has some artifacts right here, but normally you would see a bunch of values of 0 again here. But now let's look what happens when we push the phase. When we push the phase, we get a DC offset. The whole thing offsets completely. So, when the frequency we're trying to display with discrete values is exactly the sample rate at which we are sampling this signal, we will get a DC offset depending on what phase the input signal went into the sampling machine. But what happens if we push the frequency knob even higher? Suddenly, there appears to be another sign appearing, but it's much lower than the input signal. Let's fix it to 31. We mirror again at the zeroth frequency. The sample rate right now is of course 30. The Nyquist frequency therefore is 15. So if the generator is at frequency of 31, 31 goes 16 above the Nyquist frequency. So 15 minus 16 equals -1. And -1 goes 1 beyond the zeroth frequency. So 0 plus 1 gives us a frequency of 1. This is why we see exactly 1 period inside this window. Let's push it even further. The frequency rises as I push the knob higher, but it's a much lower frequency, of course, than what we have set as our input signal. Let's push it and see what happens again. At some point, the beat frequency is back. Back for the 4th time, I guess. And then we hit the frequency of 45. And again, we hit the Nyquist frequency for the 2nd time. As a matter of fact, the frequency will infinitely mirror between this Nyquist frequency and the 0th frequency, back and forth, if I push the frequency higher and higher. So when I push this higher, you will see that again, at a frequency of 55 already, we see there's a much lower sine wave appearing again. And when we push it higher and higher and higher, we will again come back to 60, which is the 0th frequency, but in its 2nd mirroring. And this is actually also the simple answer to why we can only test within the frequencies of 0. Of course, we can't go below that. And the frequency of 39. Because in this window, we have exactly 80 samples. And the Nyquist frequency, therefore, is 40. Thus, we can't test the 40th frequency because the 40th frequency is the point of ambiguity. So we can only test the 39th one. Thanks for being a part of the adventures of the discrete Fourier transform. If you have any questions or suggestions, simply leave them down below. Have a nice day. Bye.